Hello and welcome to this webinar on introduction to plate making technologies and workflow. This is a joint collaboration Esko and DuPont are having on sharing our knowledge. And to kick this session off, I would like to invite Brad from DuPont to kick the session off. So Brad, you are up.
Thank you. Good morning, good afternoon, good evening to everyone out there. We appreciate you joining in. We're excited to join in on this webinar with you, share some knowledge, have some good discussion, hopefully answer some good questions at the end as well. Just a short introduction. My name is Brad Gaskew. I'm with DuPont Cyril Solutions, so I'm a technical marketing leader for North America. Been in the technical service department for the past 7 years, so servicing customers all over North America, helping doing plate setups, problem solving in the plate room, press room, doing a lot of fingerprinting and stuff of that sort. So have a lot of good hands-on experience with customers, and so hopefully going to be able to share some good knowledge and teaching with you today. So I always like to start out when we're doing kind of a basic plate making training. I like to start out with basic terminology. So we're going to just start with some real simple terminology. Some of you might know this already. Some of you might be brand new. So we're going to make sure we all are on a same playing ground here. We all are going to know the same plate terminology. So if you look at the image here on the left, this is a finished plate. On the right is a raw plate, a raw sheet of photopolymer. So we're going to start there with the raw plate. So on the back of a plate, you're going to have a polyester base. That's just the PET that gives the plate stability. In the middle, you're going to have the photopolymer. That's most of the plate is built of the photopolymer. And then you're going to have a LAMS layer on top. That's a carbon mask that we're going to image. And then on top of that is a cover sheet. The cover sheet's just there to protect that LAMS layer during shipment, during handling before we go to the imaging process. And on the left side there, the finished plate, we have, again, the plate backing, that PET. The image area is going to be the part of the plate that collects ink from the analogs. So that's the raised surface, the face of the plate. You have the floor of the plate. That's the bottom of the plate that does not get inked. And then the distance between the floor and the image we call relief. You're going to hear me say that word a good bit this morning. It's a very critical term in flexo plate making. Then you have your shoulder, which is kind of the edge of the dots. And then caliper or gauge, which is your total thickness of the plate. So that's the basic plate terminology. You're going to hear me use a lot of these words this morning. And I think it might oh, there we go. All right, so this is common plate size formats. So these are just some basic format sizes so you can understand the size of the plates that we sell these in. So the smallest one is a 25 by 30 inch. I'm here in North America, so I'm going to say inches. All the metric numbers are here in the slides, but I'm not used to doing metrics, so I'm going to say all the standard numbers. So a 25 by 30, and then a little larger is 35, 47, then 42 by 60, and then 50, 80. We also refer to these as one number. So like the 35 by 47, we might call it 1,000. 4260 is a 2,000, and 5080 is a 3,000. So these are the formats we typically sell the plates in. Smaller plates typically use a narrow web, label market, label printing. Larger plates in more wide web flexible packaging or corrugated preprint when you need really big plates. So some common plate thicknesses, some gauges. So starting at the left, these are the thinnest plates that we have, the 030s, all the way to the bigger ones, the 250s. The 250 ones, the thicker plates, kind of like the 125, 155, 250, are used more in the corrugated industry. So the thicker the plate, typically the softer it is. So in corrugated printing, direct print, you need a really soft plate to be able to print down into the fluting of the board. And then the thinner plates are typically used more for label printers, flexible packaging, and paper printing. But the size of the plate, the thickness is going to be determined by the undercut or the pitch of your press. So all your sleeves and cylinders will be specifically designed for a certain plate thickness that you're going to run on that. And then there's some other gauges that I don't have listed here that are a little more abnormal or maybe being replaced, but this is mainly the the thicknesses that we produce plates in. So what plate should I use? So this is just a chart just for you to glance at. I'm not going to talk through it, but we have a ton of different plates of different polymers, different sizes, formats. And really, I want you just to see that on the left-hand side, there's different, you see applications. So flexible packaging, tag and label, so on. Different inks, different dot profiles, the round top or flat top, and the different durometers. So really, we have a plate type to fit whatever need you have, whatever press, whatever kind of substrate, whatever kind of ink. We can determine what plate will fit best for your application. So that's really important thing I wanted to talk about here is just looking at the variety of plates we have, but just know that whatever your application is, there's a plate out there designed specifically for that application. All right, so going into the basics of flex plate making, we're going to actually walk through each of these steps of the plate making process. And this is what I would call like the conventional or traditional plate making process that we've been using for years and years. And then at the end, we'll talk about kind of a newer way to make plates. But we're going to start out on back exposure, and then we're going to go to imaging the plates. Then we're going to go main exposure, and then we're going to process or wash out the plate. And then we're going to go drying if that's needed, if it's a solvent workflow. And then we're going to go light finishing and post exposure. So that's the process. We're going to walk through each of these steps real briefly. I'm going to just do a brief overview of every step and what happens in the step. So first is back exposure. So this is one of the most critical steps in the plate making process. This is what's going to determine the relief. I told you I would say that word a lot. So the back exposure process, the very first thing you do is going to determine the relief. And what we're going to do, if you look at this little diagram here, when I hit this button, is we're going to turn the plate over on a frame that just has bulbs on top, like you see here on this one. So the bottom of the bed has a chilled bed on it. It's cool. And then the top, you see there on top of that clamshell is a series of fluorescent tubes that produce a UV light. And so we're going to put this plate in there actually upside down. So the back of the plate is going to be facing up. And we're going to expose light through the back, the PET backing. And we're going to expose the back of the plate to create the floor. So you see here when we do the back exposure, you can see the polymers cross-linking and harden. And that's going to create the floor of the plate. And then if I come here, how we determine the back exposure time. So everything in photopolymer plate making is about time with the exposures. So you're going to have a back exposure time, a main exposure time, light finishing times, because depending on the polymer and the exposure frame and the lamps, you're going to expose that plate for a very specific amount of time every time to make sure we have a consistent plate. So we have a back exposure step test process where we're going to flip that plate over. We're going to write some determined back exposure times that we know is going to fit a window for this certain polymer. And then we're going to use some opaque material to cover the plate up and only have one area of that plate exposed at a time. So for instance, this one here would be a 20-second back exposure. So you can see all the rest of the plate's covered up. Only the 20-second lane is exposed, and we're going to expose that for 20 seconds. Then we're going to move that opaque material, and we're going to do a 24-second back exposure. So we'll do this for each step. That's why it's called a step test. We're going to make sure that the lamps are pre-warmed. So that's critical when using exposure frames that have just fluorescent tubes, is that these lamps have to be pre-warmed. Typically, we warm them to about 100 degrees Fahrenheit to make sure that the output is consistent and is kind of peaked out. Otherwise, if you start with a cold bulb, a cold lamp, the output's going to be lower, and then it's going to be very inconsistent. So we want to make sure to start with a pre-warmed exposure unit. And so what's going to happen for each of those steps, we're kind of looking at a side view now of the plate. You can see here we have the 12, 16, 20 second, 24 seconds. As you expose that plate, the longer you expose it, the thicker the floor gets. And then the thicker the floor gets, that changes the relief height. And so the more back exposure time we give it, the less relief we have. The less back exposure time, the more relief that we have. So that's how we determine our relief, is by our back exposure time. And you can see here on this chart, these are some recommended reliefs that are developed and standardized by the industry. So like with thin plates, typically 18 to 22 mils, pretty common. And then it varies as we get thicker. But we want to make sure that we develop and establish a target relief at each customer. And then that we have a back exposure time that's going to achieve that relief. And then the customer's measuring plates and making sure we're hitting that relief, and then making time adjustments to the time as necessary. This is how you measure the relief. Typically, we use a tabletop micrometer, and we'll measure the overall thickness of the plate. So we'll zero the micrometer out on the face of the plate while it's measuring the thickness. And then we'll go and measure the floor. And then that's going to do the math for us to capture relief. Or you can measure the whole thickness of the plate, measure the floor, and you minus the floor thickness from the overall caliper. That's going to give you the relief height. That's how you determine that. But it's very critical that we measure the relief on every plate that's produced to make sure it's consistent. Because the problem is if we have too much of a relief, too high of a relief, this dot gets really tall and really unstable. And as we get unstable and we go on press, this dot that should be standing up straight is actually going to start laying over. As it lays over, it gets dirty. It creates more footballs instead of dots. It'll load up with ink, and we don't want that. If we get too shallow of a relief, then we can actually start printing the floor, especially on very large presses that we have to have a little bit more impression. If the relief gets too shallow, we can actually start printing the floor of the plate. So it's very, very important to have that relief at a very specific amount, day in, day out, plate to plate, across the plate. So make sure that all the plates have the relief measured and it's consistent. So next step in the process is imaging. So first thing we have to do is we have to take our continuous tone image on the top and convert it to a 1-bit file, something that the laser can actually image. So in print, what we're doing, is we're tricking the human eye into thinking we're printing continuous tone, but we're actually just printing a series of dots. So we make the file first. We can actually check the file on the imager or on the DFS unit before we send it over to the imager to make sure it's correct, make sure the right curves are applied, the right screening is applied. If you look down further into this lin file, you can see these dots are just built out of pixels. So we build everything on the file out of pixels. The higher the resolution, the more smooth we can make dots. So that's why high resolution is nice in imaging, because we have more pixels to use here. So going to the imaging. So imaging a plate is a completely digital workflow. There's no analog process. There's no film needed. The LAMS layer, the laser ablated mask system is a carbon layer on the plate that the laser inside of the CDI is going to image for us. So you can see here in this little diagram that the laser is ablating that mask. It's kind of like a side view of the CDI. So we wrap the plate around a drum, and then there's a laser on the back side that's going to traverse and it's going to move, and that's going to fire and ablate that carbon mask. And there's a vacuum system in there that's going to suck that carbon away. And that's how we make a digital plate. This little video is going to be a little more interesting instead of just me talking about it. But you can see here, we load the plate on the CDI. It wraps it around a drum. It's a clamp system that clamps the plate. It's going to spin that plate. The laser is going to fire on the back side, and it's going to image our file onto it. And then it's going to come out, and now you can see the image is on the carbon mask. So that's imaging. Now, next step is main exposure. So the main or face exposure is what we're actually going to create the relief now. So we've developed the floor during the back exposure. We've imaged the plate. We've imaged the carbon mask. And now we're going to shine UV light through the carbon mask that we've ablated away. So where the carbon is still on the plate, you get in this diagram, the light doesn't go through that carbon. It stops. But where we've ablated that mask, where we've imaged the file, the light's going to shine through the carbon, through the openings in the carbon, and then start cross-linking that polymer underneath it. And it's going to build up into dots or in the image area. So we also have to do a main exposure step test. We have to determine the right main exposure time. Again, I said everything is done in time with exposures. So you can see in this step test, what we did is we image a series of small dots. Typically, we want to see dot failure. So we image small dots in the highlights, and then we're going to main expose it for different times. So this one is 4 minutes, 5 minutes, 6, 7, 8, 9. And then we're going to find the exposure time that develops the smallest dot possible. And then once we do that, for instance, here, this 7 and 8 minute look pretty similar. So I would go into 8 minutes to give myself a little bit of cushioning for the lamps as they start to age and the UVA output decreases. but I wouldn't go into 9 minutes because then you're overexposing the plate. You're giving too much light. We only want to give enough light to the plate to cross-link the polymer. We don't want to overexpose it. So that's how we do the main exposure step test here. What about flat top dot? So the main exposure is the process that determines if a plate's going to be round or flat top. And a round top dot is what we call like a traditional digital dot. So if you have a regular digital plate that has that carbon mask on it and you expose that plate with oxygen present, the tip of that dot will become shaped round. It'll be like a bullet shaped dot. And it's really good for like narrow web printing when we have very precise impression adjustments. But the problem is whenever you start giving that plate some squeeze, you get a lot more dot gain. And so we like a flat top dot plate now. So we can actually make a flat top plate with a digital plate with a couple of different ways. So either we can flush the surface with some kind of gas like nitrogen to push the oxygen out. We can use UV LED exposures, which have a high UVA output, and so the oxygen does not mess with the cross-link in the polymer. Or we can have plates that have built-in flat top dot technology actually into the plate. But really, the industry has moved almost all to flat top dots. It allows us to have more consistency on press when it comes to dot gain, and then it also allows us to hold super fine features, so really small dots, small text. And then allows us to hold microcell patterns in the surface really, really well. And microcells help us transfer more ink. So that's the main exposure step of the process. Now we're going to go to processing. So now that we've actually made the floor, we've imaged the plate, we've exposed it and actually created the relief, the image areas of the plate, we have to wash away now all the unexposed polymer underneath that carbon mask. A couple ways we can do that. First is the solvent processing. So this is a machine that we would load the plate into, and it has a series of brushes inside of it and the solvent. And so those brushes and the solvent are going to wash away all the unexposed polymer. It's going to break down that polymer into this solvent. We want to ensure that the washout solution is clean and that we have a certain percentage that we set it to. So typically we put it like 3 or 4% solids. It's basically measuring the viscosity of the solvent. It's determining how much polymer is in it. We don't want to get the solvent too dirty. If the solvent becomes too dirty with polymer, it's not going to wash the plate out efficiently. So we want to make sure that machine has a good solid percentage setting into it and that it's keeping that. So the solvent's clean when it washes our plates out. And then sometimes in machines, we get to set the brush height. And so we got to make sure the brush isn't getting pushed too far on the plate or getting or too far off the plate. So we want to set the brush height properly and then the washout time. So we can either set it in time or speed. So we can change the speed of how the plates pull through the machine, or we can set a determined washout time we want. A technology that DuPont has is a process called thermal processing, fast processing. So this is a solvent-free washout system. It's actually a liquid-free washout system. There's no water, no detergent, no solvent in it. What we do is we actually heat that unexposed polymer up and we actually absorb it into a material and we wick it away to pull off all the unexposed polymer. So we have fast processors in different formats. We have them smaller for the 35 by 47. We have a 42 by 60 and then a 50 by 80, a big format one as well. We have different programs in each one for different polymers. So it'll have different temperature settings, rotational speeds, rotations needed to pull the polymer off. So we got to make sure that we use the right recipe for the correct plate. And then if the adjustments are ever needed, DuPont sends in our technicians to make those adjustments. We never expect a customer to make any changes in these machines. How it works on the inside here is kind of a side view, a diagram of the fast processor. So we're going to load that plate in that's been main exposed, and it's going to be clamped on each end. You can see by these gray bars here. Make this into a laser pointer. So these gray bars are clamps here, and the plate is pulled around these rollers. And then here is a non-woven material. It's like a fabric, and it's going to wrap around a heated roller. This heated roller's going to heat the polymer up as it spins. And it's going to melt that polymer, and then it's going to absorb the melted polymer into the non-woven and pull it off the plate. and it's going to do that about 10 or 13 revolutions, depending on the plate thickness and the plate type. But it's going to pull all that into a roll, a take-up roll, and then those take-up rolls are picked up, and then we incinerate them in a plant as fuel. So it's all reused. It's a very sustainable solution. Like I said, there's no solvent, no VOCs, and there's no chemicals to have on hand. There's no steel that you need. It's a great process. So that's processing. And then now for thermal plates, since there's no liquid involved, there's no drying needed at all. So if you have solvent, though, you have some kind of liquid, we have to dry off the plate. We have to go to the drying step. While these plates are in the solvent washout, these plates are swelling. So the plates will absorb some of the solvent, and they're actually going to start swelling and changing sizes. So we have to put them in a drying system to make sure that we evaporate all the solvent out of the plate, and so the plate returns to its normal thickness. And so typically we're going to measure these or dry these in a drying drawer that's around 140 Fahrenheit, 60 degrees Celsius. We don't want to go any hotter, because if we go too hot, then the polyester backing can start changing sizes. So some people might say, oh, I want to go to a hotter drying temperature to reduce my drying times to make my processing speed faster. Well, you do that, you're going to run into registration issues because the plate's going to start changing sizes. So we don't want to get that polyester backing over about 160 Fahrenheit, about 7 degrees Celsius. So we want to keep that plate around 140 degrees in the dryer. And then the drying times are about 120 minutes, sometimes longer, sometimes a little shorter, but around 2 hours to dry the plate for. So it's a long process. So that's why that thermal process that's solvent-free is so nice, because you don't have to go through this 2-hour-long step. But it's very necessary. It's a step you cannot skip and you can't shorten. So after you dry the plate, the last step is the light finishing and post-exposure. So this is a very critical step as well. Each of these steps are very important. This one's our final step that's going to kind of cure and finish the plate up for us. It's very important. And what this is going to be a drawer typically in your exposure unit that's going to have 2 different kind of light bulbs in it. So it's going to have a UVA bulb, which is the same lamp that's used in your back and main exposure. It's going to have a UVA output, and then you're going to have a UVC. So this lamp has a different wavelength. It's a DTAC bulb. So the plate, whenever it comes out of the dryer or comes out of the fast unit, it's going to feel sticky. It's going to feel tacky. And this UVC light finishing is going to take away that tackiness, the detacking process. And so that's going to make sure that the surface of the plate does not have ink stick to it. So if you don't do your UVC properly, sometimes you can have a plate that gets ink from the analogs, and then the ink doesn't want to come off the plate. It's because the plate's too sticky. It's too tacky. So you might need more UVC time. So it's an important process to go through here. So these happen simultaneously. So typically in this unit, you have a UVA bulb, UVC, UVA, UVC, and they're going to come on at the same exact time. So it's nice. You can do the 2 processes at the same exact time. It's going to vary between 3 minutes and 10 minutes, depending on the polymer type. That's a post-exposure and DTAC. So that's the entire plate making workflow that I did really quick in about 15 minutes. That's a lot of information. So if you have questions from any of that, write them down so we can answer them at the end, or put them out in the question chat. So now that we've made a plate, how can we be sure that the plate is good before it goes to press? Because one thing we don't want to do is we don't want to send a bad plate to press. That's never good. That's going to waste plate mounting tape. It's going to waste press time. We never want to do that. That's very expensive. So we want to make sure that all the plates we make in the plate room are good before they go to press. So how do we do that? What's some tools and processes? So first is have some kind of tabletop micrometer. So something that we can measure the total thickness of the plate and the relief of the plate. We want to make sure we measure the thickness of the plate, because that's going to help us determine if the drying time was done properly. If you have a set of 7 plates for a job and they have various plate thicknesses, then someone probably shortened up that dry time and these plates aren't all the way dry. And then the relief, like I said, is the critical one. We want to make sure these plates are all hitting our target relief, typically plus or minus a couple thousandths. but we want to have a really tight control on the relief of the plate before it goes to press. And then some people try to skimp out on this and get these little handheld micrometers. We don't want to use one of those because it's just measuring the side of the plate. Really, we want something on a table that we can slide a plate underneath, and we can measure the relief and thickness around the whole sheet. So definitely it's an investment to get one of these, but you want some kind of tabletop micrometer to measure the plate. So second is run some kind of plate QC strip. So it doesn't have to be this big and elaborate. This is kind of large, but really it's not big. It's about, I think, 1 inch by 3 inches. So quite small. But you can just run a couple patches in the corner of your plate. So typically I like to tell people to put a highlight dot and then a 50% dot in that QC strip. So really you just need a QC target with 2 little patches on it. And then we're going to use those patches to make sure that our plate is good. And the way we do that is use a tool, some kind of microscope, like a Betaflex here, or there's other companies that make these microscopes that we can look at dots and we can measure the dots. So we want to look at the highlight dot, make sure it's formed properly, make sure the dots look nice, how it looks here. Make sure you can see the tip of the dot in the center of the shoulder here. You can see here, the tip is right in the middle of the shoulder. It's not to one side or the other. That tells us the dots are standing straight up and not leaning over. And then you can measure the 50% as well. And that's going to help just determine, make sure you have good clean out in your processing, make sure your main exposure is fully developing your dots. And it also tells you if the right curves are applied in pre-press. So those are the 2 things I tell everybody to do as a minimum, is to look at their highlight dots and your 50% dot to make sure the plate's good before going to press. So check the relief, the overall thickness, and then your highlight dot and your 50% to make sure you have a good plate before going to press. So next is a few kind of mandatory maintenance and checks. So really want to stay on top of the equipment PM, so the preventative maintenance. Want to make sure we schedule downtime to do maintenance. One thing you don't want is unscheduled downtime. That's very expensive. You want to schedule downtime to do maintenance on machines. Do your weekly and monthly checks. Typically, the equipment manufacturers will give you the weekly and monthly checks that you should be doing on your machine. So make sure you stay up to date on that. Have some kind of checklist that's visual in your plate room so everyone can see and make sure they're being done. You can see here on this image here on the left, this is a dirty filter in a machine that was causing the exposure lamps to overheat. So make sure if you have filters that you're keeping them clean. I know on the CDI, there's filters. You got to make sure they're clean, not clogged up. And then this is a brush actually in a washout unit that is clogged up with polymer because the machine wasn't PM'd and cleaned often enough. And then if your machine gives a warning, if you have some kind of warning signs or beeps, your machines are giving you beeps and warnings for a reason. Don't just ignore it. Don't just silent the beeping and keep working. Look and see what that alarm is. Call DuPont or Esko, whoever, say, hey, this machine's giving me an alarm. How do we fix it? How do we resolve it? Don't continue using equipment that's giving you some kind of a warning. I see that all the time, and that's never good for plate making. So exposure lamps. So like I said, we're using these fluorescent tubes. UV fluorescent tubes, they wear over time. So typically they only last about 600 to 800 hours, and then they will need replacing, sometimes shorter. So it's important to have some kind of UV meter. This is a Kuhnhast. There's other kind of meters out there, but to have some kind of UV meter that we're measuring the UVA output. Typically, we do it about monthly, but depending on how much you're using your exposure unit, you might need to do it more or less. But to measure the output across the bed, typically in 9 areas, and then you're going to set some kind of minimum. So you're going to develop an acceptable minimum output that you want to replace your lamp set. Or you can say whenever we get a 20% loss in output. So you're going to have brand new lamps. You might measure and get 20 milliwatts. Once that drops 20%, you want to replace those because it's going to start getting inconsistent as well. So make sure you measure the UVA output. The focus search is important on the CDI. This is something that Esko can train you how to do, but you're going to image this focus search test. It's going to determine if the laser's in focus. You don't have to do it that often, but it's important to do, especially if a plate ever comes off. That's the important one. If a plate is ever slung off the drum and that plate hits the laser, we want to make sure that we do a focus search to get the laser back into focus. A stain test is another quick test to make sure that the laser is fully ablating the carbon mask. So this is a file that Esko can give you, and it's just going to make sure we have enough laser power to fully knock off the carbon mask and leave no residue behind. And so this is a process you go through. You use a light table and a transmission densitometer to do this. It's very easy and simple. So some quick problem solving kind of tips. So whenever you have an issue in the plate room or press room, the important thing is to gather as much information as possible about the problem. That's really going to help you solve it and find the source of the issue. So I always tell people, just ask the right questions. Know the questions to ask to gather all the information that you need so that you can figure out the source of the problem. So that's the first thing, is ask the right questions to gather all the information that you need about the problem. And then 2, have the right tools on hand. It's really hard to problem solve unless you have the right tools. So these are the 5 tools I think it's necessary to have in the plate making room. So a tabletop micrometer, like I said, to do relief and measure caliper like you see here. A transmission densitometer, like this Teshcon DENS up here, or there's other devices that do this, but it's going to measure the light coming through the plate on a light table. And then some kind of a temperature measurement, some kind of thermometer or probe to measure the temperature of your solvent, of your drying drawers, of the fast unit. So there's all kind of temperatures involved here. So we got to make sure to monitor temperature. A UVA meter to measure the output of the lights. And then some kind of high-powered microscope like you see here. So this is just like a regular microscope, or you can use like a USB microscope, are great for taking photos. But you need to have some kind of high-powered microscope to be able to look at these dots on a plate, because they're very, very small. All right, so that's plate making and plate making QC and problem solving. And then I'm about to hand it over to Jan, but this is the conventional plate making workflow that we just went through. This is how we've made plates for years, but it is changing. So as we see all around us, incandescent lights are becoming less common and LEDs are everywhere. If you try to go to the store and buy a light bulb, everything is going to be LED. And we're seeing that in graphic arts as well. So these 2 exposure units for back and main exposure, we're going to see those go away because they're using fluorescent tubes. And then we're going to see the whole industry go to LED. So this is the XPS system from Esko. This is the future. We know LED is the future. We see that as the future at DuPont. And we even see that so much that DuPont has developed a plate family specifically for LED exposures called the Lightning Plate family. And we're going to talk about that later in the seminar coming up, I think, on May 5th. But that's just a little teaser. But I'm going to hand it over now to Jan to talk more about that.
Thank you, Brad. Thanks for that very insightful presentation. And next up is Jan, my very esteemed colleague, who will talk about the Flexo technology in general and also about the new product families we are bringing into the market.
All right. Welcome. Yeah. Good afternoon. Good morning. You can see my screen?
Cool.
Okay, excellent. My name is Jan Buchweiz, Technical Product Manager, Digital Flexo, so responsible for the hardware worldwide. I'm quite long with the company. Actually, was already with Basel Shear Laser Graphics in '82, later Baco, then and today Esko. Let me move on with the presentation. Hold on a second. Why isn't it moving? Yeah, where everything started. Actually, in 1995, we introduced, together with DuPont, so Baco DuPont, we introduced the first digital imager for photopolymer plates. Yeah, so this machine at that time had the R&D name George 2, actually. And from there, actually, we continued. Innovations are key. Innovations are the enablers for becoming or for offering today a solution which is really compatible to gravure printing and offset printing. It took us a while. A lot of steps were in between. So the selection of the right tool sets inside of the CDIs is key. Fiber laser, for example, but also the understanding that you need a high resolution imaging to be able to build up enough pixels to establish straightforward screening. In NUV, main exposure was one of the courses we did, but is also the foundation for the 2 days XPS LED exposure system. HD printing quality was in between, but in the end, what we learned from our customers is the need for automation. Yeah, more about that in a few minutes. The reliability and the consistent quality output actually made the CDIs being the workhorses in the market, resulting in the largest installed base. But also important to mention, we have a very large global sales and service team supporting you whenever there is anything to be discussed. An imager for every need. Here you see the merger out of the CDI crystal and the CDI sparks leading over to the CDI spark family, actually. So when it comes to the CDI spark family, you see that we have everything, so all the different formats. The CDI Spark 1712, also that's the A3 format, 420 by 300 millimeters, till to the CDI Spark 4835 to 1200 by 900 millimeters. The customers can select or can pick the right machine, coping their needs with their needs, meaning often addressing the correct format for their printing machine, for example. So the format of the CDIs is important. Then the customers can pick the right optics. We have different optics solutions there. And also, last but not least, the customers can pick the right productivity. The productivity depends on the tech time you need to address. Yeah, on the need, how quickly you like to have a plate. From the label market, let's move over to the label market and other applications. Other applications, what is that? Basically, laser graphics in the past was addressing all special, a lot of special solutions, because the label market, this format is also addressing, for example, the aerosol can printing, the beverage can printing, but also the plastic tub printing. For this market segments, you often need to use steel-based letterpress plates. So we offer magnetic or magnetic vacuum drums, because a lot of customers want a dual-use device, so to be able to run flexo plates for the label business, but also address special applications here. And also important to mention is we also offer CDIs with dedicated optics for security elements for up to 8,000 ppi imaging resolution. This means that you can print 1-point kanji when you ablate the plate at that high resolution. This is getting more and more interesting for customers, because the security element market is increasing, just to prevent fake products in the shelves. So we see that there's an increasing demand for this high resolution optics. Moving forward, the machines, the CDI Spark series we have for flexible packaging and corrugated. These are the CDI Spark 4835s till to the 5080s. The 4835s is quite a good fit for mid-web printing. So the printing presses we had, or we still have, but had in the past, the very wide printing formats, they are not that prominent any longer, but the mid-web format is actually increasing. But for trade shops, for example, the CDI Spark 58 is a very attractive machine, because it allows you to imposition many files on the plate and make these plates in one go. What we learned from the market, most recently from China, you see the lace chips here, for example. These are print results from China. Learning is here that especially the Chinese customers, they were looking for a solution to transfer jobs from gravure to flexo. Today, with the 2 days solutions we offer, it is possible. When you look at the samples, you only can identify it because of the fine text not being scattered, as you often see it with gravure. Yeah, when you look at fine text, you see the tiny edges over there, you know, okay, that's gravure. Yeah, and this trend moves forward, moving jobs away from gravure to flexo because of sustainability reasons. And very interesting plastic bag I will showcase during our next session, which is on May 4th. The advanced session, please join that, because the story behind that plastic bag is quite interesting to see. And last but not least, what Robert Bruce, my colleague, will talk about is also screening for corrugated, which allows a better ink lay down with less fluting, a better appearance. So in total, you see the Spark family is quite complete. We also have CDI Advanced cantilevers for sleeve imaging, so dedicated to sleeve imaging. Whenever there are any questions, please feel free to reach out to me or to Brett. I'm sure we will together can answer all your questions. So that's the first family, and the second family we introduced a while ago is the CDI Crystal family. Now you might ask, why did we bring out a new family? It's simply because we try to bring automation to, for the CDI Sparks. That's quite cumbersome if the device originally was not built for automation. So we were sitting together with with our customers. We asked very critical questions. You gave us very critical answers as well, but very good input about what is important for a machine, especially when we go for a completely new design. Ergonomics were important. Ergonomics combined with a good look. That's why we are proud that we won the Red Dot Award, the Design Award, after the introduction of the machine. But when it comes to the CDI Crystal, the result out of our investigation with our customers, was that what you want is you want a highly consistent imaging result out of the machine. That is given by the CDI Sparks, but here it's a must to offer, of course, as well. Increased quality, of course, we offer a quality level which is able to be equal to gravure and offset, yes. But it's up to you to decide on which quality level you want to output. But no doubt about that, if you output something, it must be consistent in quality. Process integration and automation is getting more and more important because it is eliminating potential operator mistakes. Yeah, so taking digitizing from the design to the actually end of the complete printing process with our family member AVT, even till to print inspection. More about that in a few slides. And last but not least, even more important than ever, is the increased simplicity and the ease of use. What we learned during the time of COVID is that, and unfortunately still, we see a lot of people being ill. So having experienced people being ill means that often the production is interrupted. This is something which should not be done. That's why we try to make the design as simple as possible. Equal to the CDI Sparks, we offer the same optic solution for these devices, so that the machines are compatible among each other. This means the output of a CDI Crystal 5080 is identical to the output of a CDI Spark, independently of the format. We often see customers who have a CDI Spark 4835, and after they grew their business, they decided to go for automation, and then they bought a CDI Crystal. Then, of course, you can get, depending on your needs, the plate format as you like it. The machine handles automatic plate loading from up to 1.5 up to 3.94 millimeters, fully automatic loading, unloading. And if you want to go for thicker plates, for example, partial plates, simply switch it to manual mode. You can do that anytime. Yeah, it's even 6.35 millimeter plates can be loaded, however, not automatically in this case. But you have always the option doing so. When it comes to the ease of use, just coming back to that, what is important for the operator, the merged file ends up in the job queue. As you can see it here, you pick the right, you choose the right file here. You can put it to the top of the list. For example, you see what plate is needed. You simply put a plate here, align it. Sensors will tell you whether the alignment is good enough. So support the operator, then you click the button and you're done with that. Yeah, the rest the system is doing on its own. So the operator is freed up to tackle all the other tasks in the plate room. At a glance, the key benefits of all CDIs, so both families, modular machine concept, size and productivity, you can pick according to your needs. Optics, just choose the optics you want to have. They are, as said, they're compatible throughout the whole portfolio. Consistent quality imaging results are a given. That's important, that any plate you do anytime is equal. And last but not least, the CDIs are fully integrated into the Esko workflow solutions. In total, we have in the meantime 4,600 images in use, actually running, producing 80% of all digital flexo plates, roughly about that. Why is that? Because the customers, the feedback of customers told us that these machines are extremely reliable, so becoming the workhorses, so the foundation of the business. And we, of course, do our utmost to stick to that and to provide further solutions which are that robust and that good. Here on the other side, you see the XPS crystal. This is the UV exposure device. And here you see that it can be connected to the CDI crystal. That was one of the reasons why we built the design as it is right now. Let us have a look onto the video. Fredrik, you will start the video? All right. Let me explain quickly what the video shows. You see here the CDI crystal 4835, and you see that there are two plates actually. On the left side, you have an additional table or a table extension where I position two plates. Why to do that? Because we don't want the operator being in time in front of the CDI to load the new plate. You see the CDI is doing everything. So what we offer the customers is that you have a second plate in place anytime while the CDI is imaging. The robot, the plate handler, is then moving the plate to the XPS crystal data. The parameters, which are predefined depending on the plate type and the plate thickness, are handed over, so the operator does not have to pick here the right plate type. If you put a plate manually onto the XPS crystal, what you can do anytime, then you just have to select the plate type and the thickness and just click the button to start the exposure. Here you see that I put a second plate on it, and here you see what is happening. Even there, the robot moves the plate automatically to the CDI. Okay. Platemaking Advanced webinar, just a short outlook to the May session. We will talk about everything regarding screening, the very helpful tool making your life a lot easier, Print Control Wizard, Flexo Engine, plate imaging, of course, we talked about that, and we will have an in-depth look into the technology of the XPS Crystal LED plate exposure. All this together with the right tools, the right screens, the right imager, the right plate, and the right UV LED exposure solution, you will benefit from plate savings, ink savings, longer or no cleaning intervals, less wastage, press utilization, and higher press uptime. But more about that May 4th. And now coming to the question and answer session.
Thank you, Jan. Right, so what we will do is we'll try to have the Q&A session for the next 10 minutes. We will try to answer the questions which have been put in chat in the first come, first serve basis. Right, so the first one is, I think this is for Brad. Do you actually have water washing available?
We actually did for a little bit, but we actually discontinued the water wash because we found that thermal plate making is just a more sustainable solution. So we decided to stick with the more sustainable solution, and we stuck with thermal plate making and discontinued water wash. So no, we do not have a water wash.
Okay. The next one is also for you, Brad. So you mentioned that a higher impression weight is required when using a larger repeat press. What's the reason for this?
So typically we just find, so as everything gets larger, typically we have more variation. Unfortunately, that's just the matter of fact. And so as you have more variation, you have to make up for that. Typically on press and impression, when it comes to impression, you have to over impress a little bit more. So as your sleeves get wider, larger and repeat, there's gonna be more variation. There's more variation in the plate, in the CI drum or the impression drum. There's more variation in the substrate from side to side of the web. So just all these variations typically result in the need for a little bit more impression. And so making sure the plate and the dot structure can handle that's very important.
Okay. And is the disposal of the plate waste included in the maintenance contract? What is the average number of waste rolls a smaller machine would use?
So the pickup rolls, yeah. So the pickup waste rolls from the fast processor is included in the contract. So we pick those up. That's all included. So once you get a whole skid or a couple skids full of those non-wovens, we'll send someone to pick them up. Plate waste itself, though, actually the waste material of plates, we don't have that in the contract. We have a program called the TR3 program where we can actually pick plate material up, use plates and plate waste, and then it's used in alternative fuels and other ways. So we can do that. It's called TR3, but the customer has to pay for the freight because it's very expensive to ship heavy plates. But the waste rolls from the fast processor is included in the contract. We take care of that. And then what's the average number of waste rolls a smaller machine? So it would depend. I think maybe they're asking how many plates you get per roll. You get typically, I think, around like 18-ish plates per roll before needing to change it out. But it's a quick change out, less than typically 5 minutes, but even faster. Once you start changing them, you can change this really quick. But I don't know. The amount of waste rolls that a smaller machine would use would just depend on your volume, how many plates you put through.
All right. Are there any more questions?
In case of questions, anytime please reach out to Brad and me, to our colleagues who are in touch with you. So we will answer all questions. So if anytime.
Yes, absolutely. Happy to help.
Okay. And again, I think there's a good question there. Is the thermal washing system better choice than the solvent one?
Oh, good question. It's more sustainable, that's for sure. It's a green option. If that's important to you, it's definitely more sustainable. Is it better? It depends on what better. If you're looking at quality, our thermal plates can be just as good as quality as a solvent plate. I think when thermal first came out many years ago, and our plates we had in the processors, we weren't quite there with the quality. But now with the recent generation of thermal processors, with our recent generation of plates, our plate quality is just as good as solvent. We have no problem. We can do 200 line screen. We can hold microcell patterns. We can do security printing with thermal. So no problem meeting or exceeding quality of solvent. But I wouldn't say it's better. It's better in different ways. More sustainable for sure, definitely.
Okay. And what would be the best practice to store the used plates?
Typically, we like plates to be stored flat. So unfortunately, flat takes up a lot of real estate, but we like plates to be stored flat and with foam in between each plate. So we ship our plates raw in the box or in the crate with foam in between each one, so you can reuse that foam and use them to stack in between all the plates, and then you can put them in boxes, drawers. There's a lot of nice vertical storage systems now that are really nice. That so they're more elevator shafts that have drawers in them, so you're not taking up a lot of real estate on your floor because the plates are being stored up and down, not across the floor. Or you can do folders. The problem with putting them in folders is sometimes if you have a plate like this, it'll end up sliding down and the bottom of the plate will curl. And so if you can put them in folders, don't overpack folders. That's the important thing. But we like them flat typically. Some people like to roll them up into drums. It's not, as nice a way to store it, but you can do that. But again, roll the plate with foam on it. Don't roll it too tightly. But flat is the way we like to see them.
Okay. Looks like we actually have a multi-parter on our hand, Brad. So the question is, what is dot gain? How can you see what the dot gain is on each plate, and how many dots are there per inch? And is there a way to check on how many dots are there in 1 inch?
Yeah. Okay. So lots of questions. And Jan, feel free to pitch in here too.
No, just yeah. Let's do together. Just start. Yeah, please.
I would say I've been answering them all. So if you want to go for it, then I can pitch in.
No, please move on.
So dot gain, I mean, there's two different kinds. There's an optical dot gain, which is when, like, if you have a dot printed on a substrate, and you look straight down onto it, it looks larger because the way the light hits it. It's an optical dot gain, and then there's a physical dot gain. That's when a dot physically grows as you are printing it. So you have a little dot on a plate. We're putting ink on top of the dot, and then we're pressing that dot against the substrate. Well, it's not perfectly pressed against the substrate to transfer the ink. It's squeezed out a little bit, and so that dot gains, and it increases in size. So that's dot gain, and you can measure that with a densitometer. So you would use this device that's measuring the reflectance of light, and you're gonna measure your solids, and then you're gonna measure the area with the halftones, the dots, and then that's gonna give you a dot area. And then if you know the specific dot area that was put into the file for that area, so say it's a 50% dot area in the file, you measure that and it's measuring a 68, then it's gaining, that 18% difference. But that's actually what you want. You want your 50 to print a 68.
Yeah. Maybe let me add to that. Dot gain, Brett showed you the round top dots. Yeah, with the round top dots, it's easy to increase the dot gain, because if you put too much impression to the dot, then it's really squeezing to the sides. That is the reason why flat top dots are so helpful. Flat top dots, however, combined with microcell structure on the surface, allows you to decrease the impression, because in the end, it's all about ink transfer from the plate to the substrate. The microcell surface structure breaks the tension of the ink, lays down easier. This helps a lot for the minimum dots, but it helps also a lot for the solids. And actually for the solids, this is standard today. You always try to increase a bit or give more impression to ensure that in the solids you transfer more ink, but automatically increasing or leading to dot gain in the minimum dots.
Yep. Yeah, definitely a flat top dot plate has a much more consistent dot gain. Consistent dot gain. Across the web, day to day is this more consistent than round top, because round top's very dependent on impression. Yeah,
controllable, yeah.
Yeah, very controllable, yeah. And then how many dots per inch? That's all depending on the file. So anywhere from 45, 65 line screen used in corrugated, all the way up to 200 plus line screen on real high-end printing.
Sure. So I think we're at the top of the hour. What I will do is we'll actually take one more question. And for the rest of the questions, please feel free to actually reach out to us. There was actually a poll as well. So for example, if you would want Esko to contact you after this webinar, if you share your contact details, we'll reach out to you again. So the next question is, what is the best way to wash a plate after press manually?
Manually. Okay, so we like these plate washers. They're awesome. These automatic plate washers, but you have to typically take the plate off the cylinder or the sleeve. There is some plate washers out there that actually you can leave the plate on a sleeve and put it into it. It's really nice. But the best way to hand wash the plate, we like using sponges. So soft sponges or some kind of soft, natural bristle brush. Some kind of brush has a really soft bristle, typically horsehair. So nothing with a nylon bristle on it that'll mess up your plates, rip dots off. So using some kind of sponge or soft brush, and then some kind of cleaner or a solvent that your ink manufacturer has helped you determine will break down the ink. So we want as little physical force applied to the plate as possible. So we want the chemistry of the cleaner or the solvent to break down the ink, but we also don't want that cleaner or solvent to break down the plate too. So you can work with us or your plate supplier, and we can do swell tests to make sure that cleaner isn't going to impact the polymer any.
All right. So again, thanks everyone who has joined this webinar, and thank you, Jan and Brad, for a very insightful conversation. And
it was our pleasure, and don't miss to register for the next session.
Looking forward.
That's gonna be fun. Yes.
Okay. Thank you.
Thank you
very much.